Saxon's Calculus Lesson 114 is about implicit differentiation for the second time. So if you jump to example 1, and I apologize that I had some trouble and it just got so messy, I just decided to scratch it and start over. So what it gives you in example 1 is find dy over dx if you were given this equation, x to the 5th plus 4xy cubed minus 3y to the 5th equals 2. All right, so ignoring my boo-boos, deriving here gives me 5x to the 4th dx plus, now I will tell you that the book handles that dx just a little touch differently. I still tend to write it and then solve it out to get to the dy over dx, but they are saying I can ignore the dx if I choose to write with the y terms dy over dx. So in the book, that's why you don't see the dx attached with it as they're working. Okay, so here we go with the dx plus. All right, then this is following, because they're multiplying an x and a y cubed, 1d2 plus 2d1. So 1 is the original 4x with the derivative of y cubed. So then that makes 3 coming down with the 4, giving us 12 with the x that I said, and then the y squared. And then I just chose to write dy, not their dy over dx. So that's 1d2 plus 2. Okay, so that is the y cubed part. And what is the derivative of the first one? Well, the derivative of 4x is 4. And since I was deriving an x term, it's got the dx with it. Now I can continue with the problem minus, and when I derive here, that's 15y to the 4th dy. And then the derivative of a number is 0. Alrighty. So now I need to rearrange the problem so that I'm working toward solving for dy over dx. These terms which had dx need to go together on one side, and the terms with dy need to go together on the other side. So I wrote my 5x to the 4th plus the 4y cubed and factored out the dx part. So like this isn't existing. This is where we're at right now with the dx equals. And then I moved the dy parts to the other side. So minus 12xy squared. And again, I'm factoring out into the parenthesis, and then since I moved it, plus 15y to the 4th, and here's the parenthesis with the dy segregated out. Then I divided by dx, which put it over here, and I slashed it, and then to get it alone, this fraction has, or this parenthesis has to be divided, so it ends up in the denominator. So I ended up with this part as the numerator, this part as the denominator, and it equals the dy over dx, which is what they wanted me to solve for. Now, when you look in the book at their answer for example 1, you see that all of the signs are different: negative, negative, positive, negative. And it's okay, you can have it either way as long as all of the signs are changed, you're fine. Then example 2, find derivative twice if x squared plus y squared equals 100. So we derive our first equation, 2x, and again, they drop the dx and they write it dy over dx, but you get the idea, plus 2y dy equals 100 goes to 0. Then I solved dy over dx by moving this, no, I think I moved this term over, which is why it was minus 2x over top of dividing by the 2y to get rid of it. Simplifying the 2's takes me down to dy over dx is negative x over y. That's my first derivative done, but remember I have to derive twice. So now I'm deriving a fraction, which means I'm following low d high minus high d low over square of what's below. So low is the y, derivative of negative x is negative 1. Again, they don't have the dx, but low d high minus high, so that's negative x over derivative of y, which is 1, and then the dy attached, over the square of whatever was below. And that's the derivative twice. Okay, so now your next job is to kind of simplify this. So it's going to negative y plus x, and then again, I've started following their dropping of the dx and putting this as dy over dx, and you'll see why in my next step over that same y squared. This dy over dx needs to be substituted for what we had found originally for the derivative, which was negative x over y. So now here I'm substituting in instead. So you see here's the negative y plus the x, substituting in this negative x over y over top of the y squared. Okay, now I still need to simplify. So separating these puts negative y over y squared, which makes it negative 1 over y if you reduce the y out. Then this part becomes negative x squared, two x's going together, over top of a y, and they're still over the y squared. And I already fixed it on this one when I separated it, but I still have to fix this one. So that implies the fraction y squared over 1. Flip it over because it's dividing, it becomes 1 over y squared. When you simplify that, you get negative x squared in the top and y cubed in the bottom. So I have here this negative 1 minus x squared, times 1, doesn't matter, and this one was still over y, and this one was over y cubed. Okay, so now I see I have a y in the denominator and a y cubed. Well, common denominator that to y cubed. So that's why I slashed this y and made it y cubed. It already had 1, it needed 2 more. So what was a 1 up top gets the y squared. So now if we simplify that, that is, and pull a negative out, negative, and you'll see y in a split second, y squared plus x squared. Oh, good grief, what was that in the original? X squared plus y squared equals 100. So substitute that for 100 so that you basically get negative 100 over top of y cubed. Now, I had originally had this equal to the double derivative, and then I just chose to box it this way, saving me writing it a second time, but you get the idea there. Now, example 3. Yes. Double derivative again if 2x cubed minus 3y squared equals 7. Start off with the original derivative, so that becomes 6x squared. Again, they don't use the dx. So this time I decided, oh, I'm just going to stop fighting them. I just decided to ignore it. Minus 6y with the dy over dx, and the 7 goes to a 0. All right, so solve for dy over dx. With a little bit of manipulation, you see moving the negative 6x squared over, dividing by the negative 6, cancels off the negatives, cancels off the 6's, and I get to keep x squared over y. All right, now, obviously deriving a second time, and again, it's a fraction, so low d high minus high d low over square of what's below. So here's your second derivative. Low one, derivative of the top, minus the x squared, derivative of y is 1. I did keep the dy over dx with that. And then I said, well, even though I knew, well, I went ahead and finished writing over top a square of what's below, so that made y squared. Then I substituted this as the original equation, x squared over y. So now here is the derivative piece dropped down. This is 2xy organized minus, and then x squared times x squared is x to the 4th over top of y, and it's all over top of y squared. Now the last time they simplified that by separating it into two different fractions and manipulating this, and you can do so, but since they chose to stop it there, I was like, well, why do extra work that is not exactly necessary? And that was, just a second, I'm trying to find which example that was again. Actually, wait a minute, maybe I did stop it too soon. I'm double checking. 2xy minus, they did simplify it another step. Hang on, I've boxed too soon. Ooh, let's fix that. Okay, so 2xy squared, because I'm adding a y here, minus the x to the 4th, and it already had its y, so no change, and then flipping y squared, so 1 over y squared. That's going to give us 2xy squared minus x to the 4th over top of y cubed. Is that where they stopped it? 2xy squared minus x to the 4th. That's, okay, there we go. They did simplify it a little bit more, so that is not supposed to be boxed. And it equals, obviously, the d2y over dx squared. Okay, that, there is still example 4. Which says if 4y squared equals x cubed, use implicit differentiation to derive twice. Okay, so we start off with our 8y dy over dx equals, and then this one becomes 3x squared, and I chose to not put the dx with it. Simplifying for the dy over dx gives me 3x squared divided by the 8y. Nothing I can do to simplify there. So now deriving, Again, following low 8y, derivative of the top 6x. And because I was deriving an x, I left it. Low d high minus high, rewritten 3x squared, derivative of 8y is 8. Wrote the dy over dx, knew that I needed to substitute that for this equation, so I went ahead and put it in over top of square of what's below, 8y squared. Okay, then the simplification became a little fun. Obviously, 8 times 6, 48xy, minus 3 with the 3 made the 9, x squared made x4, all over top of the y, and the 8 canceled off and left the y, okay, and then the, yes, and then 8y squared was 64y squared. Okay, I still wasn't finished simplifying because common denominator made a y, put a y here, added another y here, which made it y squared. So now I'm at 48x y squared minus the 9x to the 4th over top of y, flipping with the bottom fraction, 1 over 64y squared. Now I get 48xy squared, no change, minus the 9x to the 4th over top of 64y cubed. Now, the book said you can stop the answer here, which would have been really nice. However, because the originals, like this could be factored into parts that mirror the original, then I could do more substitutions with the originals. All right, so the book does it both ways to show you that eventually you get down to this answer both ways. I chose to only show you one, but before I even go through that, they do make a clarification that, where was that? I think it's on the next page. Yes, this answer is correct. However, we can make the substitutions. Had we tried to simplify example 3, we could have worked for a long time and not come up with a simplification. So how are you supposed to know when you're supposed to change what is an okay answer into manipulating it with something from its original? Well, they say this. The last step in problems like these is not calculus, but an algebraic game playing. Sometimes the result can be simplified and sometimes it cannot. So again, you just would have to play with it. That's why they called it algebraic game playing. I didn't find it a fun game necessarily, but you get the idea. So you can try and see. I think the general rule of thumb is if it looks like the parts you have here are factorable, then try and see if you can manipulate it back to the original. If it's not something that looks like it's easily factorable, I would just leave this where it was as they had to do in example 3. Okay, so moving on then. And I had a little trouble because I kept wanting to substitute the wrong things, but I was trying to substitute to the same letter in most cases. So my 48xy squared can split a 4 out of 48, leaving a 12. Pulling a y squared out left the extra x. So that was this fixed. Then I moved on to the 9, and I realized x to the 4th could be written as, and again, I thought, oh, maybe I'm going to substitute here. So I pulled an x cubed that left the extra x alone out here with the 9. And then in the bottom, 64, again, I took 4 out with the y squared, and that left me with the 16. And since I pulled 2 y's, I had an extra y left over. Okay, so now I've factored it. What can I substitute? So instead of the 4y squared, I'm writing an x cubed with the 12x. That was easy enough. Minus 9x. And then again, I started to substitute for the 4y squared, and I realized, wait a second. That's introducing a y again that I probably don't want. So I put it back at x cubed. In the bottom, the 16y, couldn't do anything with that, but that 4y squared I could plug in as an x cubed. Now you'll argue my last statement up here about x's and y's doesn't hold because I already have a y here, but I can't make them all go away, and this was not a substitution I could do. And putting the y up here just looked like it was making a mess. So again, I left it. So this simplified to 12, x to the 4th minus 9x to the 4th. Oh, hallelujah. That's why I wanted to do that then. Because, and so I could have left this unfactored, because ultimately it went back to the x to the fourth, which is what I ended up with here, which is how I can combine them. That's why it was a good thing. So 12 minus 9 left me 3x to the fourth, and then in this bottom, of course, it was 16y with x cubed. So now that I'm here, the x3 and 3 of these x's will cancel, so that just leaves me a single x in the top, so 3x with the 16 and the y, and all of those x's canceled off, and that was the answer that they got. So if you had worked the other way and substituted in more for like separating, factoring out x cubes, and then plugging in 4y squareds for that. And the other reason why that's messier is because it inserts a coefficient where there didn't used to be one. But it will still work, and you can follow it in the book the way they did it, working all the way down to 3x over 16y.